All right, this will be the first chapter for exam 3 of chapter 21, which will be on electromagnetic induction. And Faraday's law. And this is also related to labs 7 and 8. Right? So this one is on Faraday, and this is the one where I do the actual demonstration, and this is a lab that's using the simulation using the FET program. So 7 and 8 will open up later in this next week. So this will be for part of exams 3, which will be on chapter 21 and 22. So electromagnetic induction, induced EMF, they talk about it here. And what it means, all right, we talked about how a current, okay, so I have a current going through a wire. It will produce, so if I have a current I, it'll produce a magnetic field looping around it. So if it goes this way, it'll do a loop. So if I point it out this way, we have a magnetic field going out. So a magnetic field, so a current moving charge produces B, right? And again, B is in the SI units are Tesla, but then we use Gauss, and we have 1 Tesla is 10 to the 4th Gauss. So that's what we have from the earlier chapters. Now we're going to be looking at what happens if we have a magnetic field. Can we do the other way around? So if we have a current or moving charge producing a magnetic field, can we produce a current using a magnetic field? And the answer is yes, but it's a little complicated as far as how it works. So I will erase this. And the way we can do this is, as we've seen earlier, if we have a current, the magnetic field in a coil is go by mu naught N I over L, where N is the number of turns, L is the length. So the more turns per length times this constant times I, we get a greater magnetic field produced inside this coil. All right, so we're gonna be using a coil and see if we can produce a magnetic field current there. So we take this, we have an already made magnet, which is this is a standard permanent magnet, and what we'll do is just leave this next to this coil, and you can see what happens, nothing. So if there's no change in magnetic field, or what we call magnetic flux going through this, nothing happens. The only time we see something happen is if we move the magnet either towards it goes one direction, or away, it goes the other way. So moving it in and out, forward or backward, we produce a current in this wire, which we pick up in this galvanometer. So that's how we can produce a current. We'll see this is the principle of a generator. Nothing happens if it's not moving, and the faster we move it, we get a bigger current. So that's the principle we call Faraday's law, as far as that's concerned. I'll write this cellular volume here and go from there. So the way we define this number is we define, we call voltage, induced voltage, induced I should say. All right, we get induced voltage in this wire, which leads to a current. And we call this induced current. The book uses this term, little EMF. So we call it EMF, electromagnetic force. So it's an induced voltage. And it's defined as the change in flux, or the Greek letter phi. So flux comes from an old term. And it's actually defined as how much current, how much magnetic field current flows through this coil inside of it over change in time. All right? And so that's how it's defined as, but to get it a little bit better, we're only going to be doing two different things. So the only way we can do this, there's two ways we can change this. We define flux as B times the area. All right? So we either have magnetic field and we have the area. And times the number of turns. So we can either change one or the other. So we can change the magnetic field. Can't really do that here. I mean, I change the magnetic field by having this farther out. So, or I can change the area this thing is exposed to by rotating this coil. So what it means is, as this coil this way, very little magnetic field is flowing through it. When it's like this, it's that way. And so we define this voltage or EMF as N, either N times the change, A times the change in magnetic field over change of time, or B times change of area over change of time. For the most part, we're going to be using just this expression. So how fast we change the magnetic field over time. So how fast this changes will give us what we call an induced voltage or an induced EMF. So we're pretty much going to be doing this with a qualitative basis as far as that's concerned. And if you look at let's look at an area. Let's look at an example like this and see what we can do. So we have, let's do this example. So we have N is 3,400. A, it's approximately it's approximately 10 centimeters by 10 centimeters. So I'll take this to be a square. So the area A is 0.1 times 0.1, which is 0.01 meters squared. All right. Now we're going to have, I don't know what the magnetic field from here is. It's a pretty strong compass. It's a pretty strong magnet. And again, the Earth's magnetic field. Earth's field is about half a Gauss, or about 5 times 10 to the minus 5th Tesla. All right? So if we say this is 1,000 times stronger than that, let's say B for this part, B is 1,000 times, let's say 0.01 Tesla, all right? So now let's try and change this in, now this is not actually going to measure voltage. What this does, this measures current actually flowing here. So this produces a voltage, there's resistance to the wire which produces a current. So let's try and move this. Let's say I do it in 1/10 of a second. Pull it out. So change in time, delta T is 0.1 second. What kind of voltage would I actually produce? All right. So this will be 3,400 times 0.01 times, now we're going to change the magnetic field from this down to 0. So that's a change of 0.01 Tesla in 0.1 seconds. Right, so that's going to be, let's see, 10 to the minus second, 10, it's going to be, this would be 3.4 volts. So approximately 3.4 volts, which is probably about right for this thing. So as this pulls out, the faster I do it. So if I do it slowly, all right, so if I only do it in say 1 second, then this will be 0.34 volts. If I do it faster, if I do it in 1/100th of a second, it'll be 10 times that. So it depends on number of turns, the area, and the change of magnetic field change in time. So that's what we call induced EMF, right? So that's one way of producing a voltage or current, is by moving the magnet out. Now we can see this kind of current, as it goes in it, you can see it goes back and forth, all right? This current produced is what we call, I'll leave this up here for a minute. So that's the important expression here. All right, I'll move on. This is what we call, this kind of current produced is alternating current, or AC current. And this is based on, you can see, because it goes back and forth, right? And if we go in time, and we've already talked about this briefly, the current, the voltage, or the current does this. So in time, current. So this would be what the current is produced. And that's what we call an alternating current. And this is the principle behind a generator, right? If you ever seen a big generator, here's like a generator. What you have is, like at some power plant, is you have a coils, very large coils. You have a magnetic field, a magnet that is rotating inside the coil. And so as it rotates, it'll produce a current in the coil, which produces power. So the question is, how do you turn that magnet? Well, you have to do it some way, and that's the whole principle of a power generator. All right? And the way this works is you have something that turns the magnets inside the coil. So you have a magnet inside, and you got a generator. So if you ever go, let's say, the power plant, like for me, nearby is a Boswell power plant, Cohasset, you have a generator probably 10, 15 meters in diameter, and it's rotating 60 times per second. So it has a frequency of 60 hertz rotating 60 times a second. And so you got to turn that magnet in there. How do you do that? Well, that's the whole principle of the coal-fired plant or anything, is to produce heat, which turns water into steam, and that steam turns a generator, which then produces power. AC power. And whether it's a coal-fired plant, gas-fired plant, nuclear power plant, the whole point is to get a coil, a magnet rotating in a large coil, very large coil, not this thing, very quickly, and you can generate large amounts of power, right? And so you end up with this AC current. So, what does that mean? All right. Now, here's a picture. It's a picture in the book, which is pretty good, showing a power generator. Okay. And what you see there is a power plant hooked up to what we call a transformer, which then produces voltage, which then comes down. And the question is, why do we do that? All right. So this generator, so say a generator, a very good generator, produces power. It might be 100 megawatt, 1,000 megawatts, 10 to the ninth watts. So that's a gigawatt of power. It's a huge power plant. And it will produce it at a certain voltage times a certain current. So that power, as we've seen from this is voltage, this is current. And it'll be an AC current. All right, so if you have, say, a gigawatt of power, and let's do something a little easier to deal with. Let's have it, let's see. Let's try, to not have such a lot. Let's deal with 1 megawatt. So 1 megawatt, which is 10 to the 6th watts of power. All right? Now, our voltage, we have household voltage is 120 volts. All right? All right, so let's do this a little bit easier for me. Let's say we're doing 1.2 times 10 to the 6th watts. So that would be 1.2 megawatts, all right? If we deliver that power at 120 volts, all right, so if the power is that, megawatts, so that's 1.2 times 10 to the 6th, and we deliver that voltage at 120 volts, that's how much current will come out, right? That's how much current is being delivered, is 120 volts, that kind of current. Divide both sides by 120, and I believe you end up with I is 10,000 amps, right? So 10 to the 4th times, yeah, that'll be the current. All right, which seems like a lot, but it's like, what's the big deal? All right, now if you have a real power line, transformer, they show here, a transformer, but sometimes these can be very, very long. I mean, you're not having the power plant right next to your house. Power plant may be 50, 60, 100 miles away. So the question is, what's the reality of that? Now, what we have happening is that in a real wire, let's keep this up. Our power is that. All right, let me rewrite this a little bit. So, power is 1.2 megawatts, V is 120 volts, I is 10,000 amps. All right, now in a real power line, if you ever see them, say we have one that's a 1 mile long. the resistance in that wire might be as small as 1 ohm. That's a very small number, all right? And well, it's not that big a deal. But in any wire, the power dissipated, or what we call Joule heating, because basically this is the principle behind incandescent bulb, is the power dissipated, P, goes as I squared R. Right? Now again, our power here is voltage times current. So any wire that has a real resistance will dissipate energy. So in this case, for a one mile stretch, if it's only 1 ohm, the power will be 10,000 squared times 1, which is 10 to the 8th watts, which is 100 megawatts. Well, that's almost 100 times that, which would mean that you would lose 100 times energy just by heating the water. Well, this is not going to work. First of all, the water would glow, and it's not very efficient if you lose 99% of the power, 99% lost in this kind of situation. So how do we do that? All right. Well, the way you do that is using what we call a transformer. All right. And here's our expression for Joule loss. This is our expression for power delivered. All right. And we want to keep that high, but keep that very low. So I'll leave that up for a minute. So this is if we have a situation here, power right here, I squared R is 10 to the 8th watts. All right. Okay. So we'll try this a little differently. Transformer. What's a transformer? Well, the thing about AC current is that you can, what we call step up and step down the voltage using a transformer very easily. And the way to do that is to have, say, a iron core in a loop, right? And you have a certain number of turns coming in. Say N is 10. And then coming out, say N1, N2 is 100. Then, and if this is some voltage 1 coming in, and it turns out the ratio of the voltage coming out, 2, over the ratio coming in is N2 over N1. So the ratio, this is what we call, and if it's greater than that, if N2 is greater than N1, it's what we call step up. If N2 is less than N1, it's step down. And there's almost no loss of energy here. It's an extremely good way of changing voltage efficiently. So you have just an iron piece, voltage coming in, again, it's all AC. And so that the voltage coming out is proportional to the ratio of the turns. So what can we do here? So say we want an example then Instead of 120 volts, all right, let's do ratio. We come in at 120, all right? Instead of that, we want it to come out at, say, 1,000 times that, 120,000 volts. In that case, we would have then, this would be 120,000 over 120, which is 1,000, is N2 over 10. So if you had 10 coming in, then N2 would be 10,000 turns. So you'd have 10 coming in here, you'd have 10,000 coming out. Now in a real transformer, you wouldn't go quite so abrupt. You might go whatever they produce. You don't have that drastic a change. In a real power plant, as we're going to see, you have the original power is delivered very high. It gets stepped up to very high voltage and then comes down, and they do it gradually, so you don't have this huge ratio of turns. Anyway, but that's the same principle. So we do this transform. So what we do then is the power plant, we transform it up to 120,000 volts and send it down. All right, so I'll leave this up. This is our rate expression for here. Again, ratio of voltage is rate 2 is what's coming out, 1 is what's coming in. All right. So what do we have here now? So we're still trying to deliver 1.2 megawatts. Well, in this case, our voltage is 120,000 volts. What will be our I in this case, right? P equals V times I. So I will be 1.2 which should be 10 amps. Same power, but at 10 amps. All right, now we're back to our same power line where R is 1 ohm. The loss then, I squared R, in this case, will be 10 squared times 1, which is just 100 watts. So instead of 99% being lost, we have less than 1%. And that's the reason for having high voltage power lines, is you can transmit a lot of power very efficiently using real wires. Now, if you had superconducting wires which have no resistance, then you could transmit any voltage you want. But that's what we have there. And that is all I'm going to be doing for chapter 21. All right, there's other parts in there on inductance. We're not going to be doing that. Inductance is part of more advanced course. So here's our power delivered. Here's our energy loss based on a real circuit. And we use a transformer to step it up using that ratio of turns. V2 over V1 equals N2 over N1. And that's chapter 21. All right, so that's it for there. Again, it's for lab 7 and 8, and answer the questions for that.